In this video, we're going to look at tables and how to get information from them. And sometimes you'll get numerical surprises where the data doesn't seem to add up correctly or something like that. So you get something of a paradoxical situation sometimes. And that's what these are intended to show. So this first example right here tells us the table shows the number of hits and the number of bats between Derek Jeter and David Justice for 1995 and 1996. So if you look at this table, the first question asked, and this is the way the questions are going to be. They're going to ask you questions analyzing the information in the table. So let's take a look at this first one here. Which player had a higher batting average in both 1995 and 1996? So if you look, in 1995, David Justice had a higher average. And in 1996, David Justice also had a higher average. So for both 1995 and 1996, David Justice would be the correct answer for that. Now, overall, though, which is number B, compute the batting average for each player for the 2 years combined. So if I want to do the 2 years combined, I'm going to do a thing like this. I'm going to have the at-bats, and we want the hits, and we want Derek Jeter and Justice. So let's start with the hits that Jeter had. Jeter had 12 hits plus 183 hits for a total of 195 hits. His total at-bats were 48 plus 582. That is 630. Now let's move over to David Justice. His total number of hits were 104 plus 45, so that's 149. And his at-bats were 411 plus 140. So that's 551. Now to get the overall batting averages for Jeter, you're going to take 195 divided by 630. Now baseball does not use percentages. They just use straight up 3 decimals to describe batting averages. So this is the 2-year batting average for Derek Jeter. So 195 divided by 630. Enter. Now, I'm not going to multiply by 100% here. I'm going to round to 3 decimal places. In here, I have 0.3095. So I'm going to round that to 0.310. And they don't put the 0 before that. So when I put my answer, I won't bother doing that. But it looks like Derek Jeter then had a 0.310 batting average. And then David Justice would be 149 out of 551. To 3 decimal places for Justice, I get an average of 0.270. So that's what they want here, 0.270. Which player had the higher combined batting average? Well, we can see now it's going to be Derek Jeter. So the paradox here was that in both seasons, David Justice did better, but yet overall, Jeter did better. And that all has to do with this over here. The times when Jeter was doing bad, that's a small number of at-bats. His large number of at-bats, he did well. For Justice, he had a large number of bats where he was around 250, and then he only had a very small number where he was above 300. So it's the fact that there's too few bad numbers for Jeter to bring his average down that much overall, and there's too few good years for David Justice for his overall average to be better than Derek Jeter's. Let's take a look at the last thing. Briefly explain why the 2 results may be paradoxical. Well, I just said, if we would expect that if David Justice did better in both seasons, a better batting average in both seasons, you would expect him to have a higher overall batting average than Derek Jeter. But as we see, that's not the case. So let's see what my options are here. When the two seasons are taken separately, the data show that David Justice is the better hitter in both seasons. We saw that. And then when the two seasons are taken together, the data shows that Derek Jeter is the better overall hitter. Here's our next example. Consider the table comparing the grade averages and mathematics SAT scores of sampled high school students in 1988 and in 1998. So this tells the grades and the corresponding scores, but it shows the percentage of students who got these scores. So let's take a look and see what we can gain from this table. Part A, in general terms, how did the SAT scores of the students in the 5 grade categories change between 1988 and 1998? It's asking for the scores, so I'm looking at this side of the table over here. So when I look at between 1988 and 1998, I see the scores all went down, all of them. These are the overall numbers, but in each category, in the 5 grade categories, all of the scores went down. So the average scores in all categories decreased. See if I can keep most of that there. How did the overall SAT score change between 1988 and 1998? So here, the overall was positive. It increased. So the overall SAT score increased. There's the paradox. Even though it decreased in all the years, it always has to do with the number of people involved. Briefly explain why the results might seem surprising or paradoxical. The change of the overall average score was the opposite of the change in each category. Well, that is true. Let's see if there's one that's a better selection here. And we might be able to select more than one of these. While the average scores changed in all categories, the overall average score did not. We know that's not true. Let's go to C. The change of the overall average score was much greater than the change in any one category. I don't know, 13 versus these. It is more. Is it a lot more? I don't know. I kind of like that answer there. I might answer C as well as A, since the change in the overall average score was the opposite of the change in each category. Now let's do this D. While the average scores did not change in any category, so we can stop right there. So our only possible answers are A and C. And it took off my A choice. Let's take a look here. The change of the overall average score was the opposite of the change in each category. Certainly, the change was decreasing in all of these categories, but it was increasing here. The change of the overall average score was much greater than the change in any one category. Well, I don't know. It sounds to me 13 is a lot more than 5 or 4. But I'm going to have to go with A. If I had to choose one choice, I would choose A. But if I were allowed a second choice, I would choose C. So let's kind of do it this way. I'm going to do just sort of like a little bitty circle there. Here we have a table of deaths due to tuberculosis. 2 different cities are presented, and they're broken down according to white and black deaths. So there are always in these, they're going to be giving you some tasks to do, like figuring out some numbers. So let's take a look at part A. It says the death rate for whites is, and we're talking about in city A. So when we're talking about the white and black death rates, we should take, this would be for the white. So for that computation, we want to do 85 over 4,690,000. So we'll take the 8,500 over the 4,690,000, and then that final answer, multiply it by 100%. I get about 0.18%. Let me see what they expect for that. So it says rounded to the nearest 100th as needed. So this is 0.18%. Now the black death rate is going to involve these numbers here. So we're going to have 600 over 92,000 times 100%. To 2 decimal places, I get 6.52%. And then the death rates for all the residents, that's where we take this number. This is the total. So from the final part, we'll take 9,100 divided by 4,782,000 and multiply it by 100%. Here to 2 decimal places, I get 0.19%. Now notice that it's closer to the white death rate than the black death rate because there were so many more white citizens in this city than black citizens. Now I'm guessing they're also going to do the same for City B. They are. For City B, here's what I want to do. Take 110 over 82,000 for the white death rates. 82,000. Nope, I did it the wrong way. 110 divided by 82,000. Multiply by 100. And it looks like 0.13%. Zero. For the black population in City B, I'm going to do 160 over 46,000. 160 divided by 46,000 and multiply by 100. And to 2 decimal places, I get 0.35. So much better situation for the black population in City B. The overall death rate then is going to be this right here, 270 out of 128,000. Multiply by 100. I did the wrong thing there. Let's see if it fixed it. It did. So 0.21%. Explain the apparent inconsistency in these results. The death rate for both whites and blacks was higher in which city? Let's see. In City A, the death rate was higher for whites. The death rate was much higher for blacks. So in City A, that was higher. Then in City B. Yet the overall death rate was higher in, so the overall death rate was higher in City B. Let me pull this over to make sure. Okay, because I ran off the page. So yet the overall death rate was higher in City B than in City A. And now let's answer the last question. This is because the population percentage of blacks was significantly blank in city A than in city B. Was the percentage of black residents was much lower in city A than it was in city B. I just discovered a mistake that I had made in this problem. It is in here. My decimal was off. Let me recheck that number. Let me bring my calculator back up. I'm looking at this one right here. That one right there is what I'm looking at. I think I'm off by a factor of 10, so let me check it out. We had 600 divided by 92,000. I think I might have only done 100. I don't remember. And then I'm going to multiply by 100. So make your adjustment here. This is actually 0.65%. Let me go ahead and fix that. This next example we have, the table is not to the right, it's underneath. I had to move things around. It's based on the assumption that 1% of breast cancers are malignant. It also assumes that mammogram screening is 85% accurate. Let's complete parts A through C. So if this table lists positive mammogram and tumor is malignant, that means the test successfully showed these 85 people to have it. Now over here, the negative mammogram means it was successful here. Suppose a patient has a positive mammogram. What is the chance that she really has cancer? So a positive mammogram, that was 1,349 people total. Which of these have cancer? Well, 85 of them do. So for part A, I'm going to take 85 over 1,349 and multiply it by 100%. I get 6.3%. Let me see how they want the answer done. So it says rounded to the nearest tenth. Okay, 6.3. Part B, it's asking us, what is the chance of a positive mammogram given that the patient has cancer? Well, these are the patients that have cancer, and these are the ones that have a positive mammogram. I think you'll find that this equals 85%. Suppose that a patient has a negative mammogram. That's this row down here. What is the chance that he actually does have cancer? So this is our total here, and this is the number that actually have cancer. So part C, we're going to take 15 divided by 8651 and multiply it by 100%. I get 0.17. It says, I have 0.17. It says type an integer or rounded to the nearest 100th. Okay, so 0.17. Those are the numbers that I get. So this example didn't really do a lot of analysis. It just had you do your computations and check your ability to do that kind of work. Here's another test that's given to people to find whether they're taking performance-enhancing drugs or not. So we have a test that detects that's 80% accurate. It will correctly detect 80% of the people who use such drugs and will correctly detect 80% of those who do not. Suppose that 10% of the 800 athletes at a major meet have actually taken performance-enhancing drugs. So that's these 80 people right here. And all athletes are given the drug test. So that's the 800 here. Then we're to complete parts A through C. So let's start with this. The table shows a total of blank athletes being tested. Well, that's just the 800 that's down here. The total number of athletes using performance-enhancing drugs is 80. Which is blank percent of the total athletes tested. So 80 divided by 800 equals 0.10. So that does verify the 10% that they suggested did. The test correctly detected blank athletes using, so let's see, it correctly detected 64, which is 64 out of 80 is the total number of using, which is blank percent of the total athletes using. I've made a mistake here. That's 64 out of 800. So let's do that one. Times 100%. And I believe that's going to be 8%. The test correctly detected blank athletes not using. Let me pull to the side. It correctly detected 5. So these are the ones that correctly detected of the users. And these are the ones that correctly detected of the non-users. That's 576. Which is blank percent of the total athletes not using. So this here, the total athletes not using, which is out of 720. That there is going to be 80%. Well, it sure looks like it fits according to that. Do I have anything else to fill here? Therefore, the table is blank with the information given. Oh, I'll say agrees with it. There's a mistake here. Total athletes using. So that should have been 64 out of only 80. Let me change this to 80. Which, if we divide that by 8, we get 8 out of 10, so 80% here. So yeah, that certainly looks like it agrees, as I said. Now let's move on to the next. How many athletes in total were accused of using performance-enhancing drugs? That's the test finds drug use. That means 208 of them were accused. These were the accused. So there's 208 of them. Of those accused, how many were actually using? Well, we have 64 out of 208. Of those accused, blank athletes were not using. So of those accused, 144 were not using. The percentage of those accused of using who were falsely accused. So these people here, this 144 out of 208 are the percentage of people that were falsely accused. So we have 144 out of 208, and then multiply by 100%. I get 69.23%. And I can see it says round it to one decimal place, so I want to do 69.2%. And then part C, how many athletes in total are cleared of using performance-enhancing drugs? So cleared, that would be these 592 are the cleared ones. Of those cleared, so I'm talking about just this row now, just this row. These are the ones that are cleared. Just that row. Of those cleared, blank athletes were actually using drugs. How many athletes were actually using drugs here? 16 of them. The percentage of those cleared who are actually using drugs is, so we're going to have 16 over 592 times 100%. To one decimal place, I get 2.7%. This agrees and does not agree. That's not even part of this. That was question number 1. So somehow I copied question 1 twice. So we don't worry about that. We'll move on to the next problem. Here we have an example of the accuracy of a polygraph test. Here it says the results in the accompanying table are from experiments on the results of polygraph tests. In each test, it was known whether the subject lied. So they agreed on statements to make beforehand that were lies and those to make that were true. So the table indicates when the polygraph test was correct, completes parts A and B below. Well, let's start here with when it was actually telling correctly what was going on. So in this first row, the polygraph said that they were lying. That means these are correctly identified because these are the people that were lying. On the other hand, this one is correct for the second part because it did correctly identify those 44 as not lying. So let's take a look. How many people did the test? So it says, how many subjects did the test find to be lying? So there were blank subjects that were found to be lying. The test tells us there was this 15 plus 40 for a total of 55 people that the test says were liars, of which blank were actually lying. Well, 40 of them. And I'll have to move to the side. And blank were telling the truth, 15. The percentage of those who were found to be lying but were not actually lying was what percent? So for this one here, these were the ones not actually found to be lying, so it's 15 out of a total of 55. And it tells us to round this to the nearest whole number. Okay. So even just to one decimal, it would be 27.3, but it wants no decimals, so I'm just going to put 27. How many people did the test find to be telling the truth? Well, that's down here. That's 44 plus 14 is 58. So 58 subjects were found to be telling the truth, of which blank were actually telling the truth. 14 of them, 44 were actually telling the truth. The percentage of those who were found to be telling the truth and were actually being truthful was, for this one, we're going to take the 44 out of 58. And it wants us to round to the nearest whole number just as before. Here I've got 75.9% if I round to one decimal place. That means I should round to 76% for the whole thing. Here we have two college teams, and their records are kept home and away. Oddly enough, both of these college teams are worse at home than they are away, which is unusual. So here's the gist behind this problem here. Suppose you're a fan of College A. You want to try to indicate to people that College A is the better of the two teams. So you're going to look at this by its percentages. So let's take a look at what my options are here. The percentages, let me see, it says College A won about 34.5% of their home games and about 75% of their away games. So let me check that out. So they tell me this here was 34.5%. Let me check that out and see if that's true. So we have 10 wins divided by 29 games. And then I'll multiply by 100 to get a percent. So one decimal place, this is 34.5%. And this 12 wins out of and 4 losses, you get this by doing 12, let's do 12, divided by 16 total games. And I can tell this is going to be 75%. So those numbers are correct. Whereas College B only won 32.1% of their home games. So let's check this out. So here you have 9 wins out of 28 games. 9 wins out of 28 games. And that's 32.1%. Yeah. That's so it matches theirs. And then about 73.7% of their away games. So here I'm going to look at 56 out of a total of 76. So 56 divided by 76. And I'll multiply by 100. And that does round to 73.7%. Very good. Let's take a look at some of the other options here. So these numbers are accurate. Let's take a look here. So it looks like College A won 34% of their home games and 75% of their away games. That was better than both percentages for College B. So we could look at it that way. Here, if you look at College A lost only 23 games, whereas College B lost 39 games, you can't use that because they played different number of games. And that's the same thing here. They played a different number of home games. So you can't directly compare them. When you come to percentages, though, those are things that you can compare. So option A is our best choice for that one. Now, consider yourself a fan for College B, and you want to prove that their percentages is better than the other one. Well, what you could do in their case is you could take the total of 65 wins and have 39 losses versus this other team, which is 22 wins and 23 losses. Now you can see this team wins more than 50% of their games, and this team wins less than 50% of their games. So, but they played a different number of games total, so I don't want to go by games. Here there's 100 games here, and there's only 45 here. So once again, I think the best idea is to go to the percentages. Let's just check and make sure they're correct. Let's see if College B actually did win 62.5% of the games played. So 65 plus 39 is 104. So I'm going to take 65 over 104. And let's see what that gives us. That is going to be 62.5%. Very good. And then Team A only won 48.9%. So I'm going to try 22 out of 45. So this one here was 62.5%. And the other one is 22 wins out of 45 losses. Multiply that by 100% to get us that percentage as well. (22) divided by 45. That's 0.4. Well, let me multiply by 100. If I round that to one decimal place, that will be 48.9% of the games played. That is true. Let's see, which claim is the better claim to you? Oh, I forgot to put a dot here. Which claim is the better claim? A or B? Well, I think B is because it's talking about the total number of games. Anytime you have more comparisons to use, the more accuracy you're going to get. And then Y, because it's based on the total number of games played.